Hi everyone. We're going to start a new unit, which is composed of 2 chapters, 27 and 28. And we're basically going to start talking about magnetic forces and fields. So the first half of this course, we talked about electric fields. And now we're going to move on and talk about magnetic fields. And electromagnetic fields are basically make up everything that is around us. We constantly are interacting with electromagnetic fields. We're using electromagnetic fields to communicate, to transmit information. So we're going to be talking about now the magnetic part of electromagnetic fields, and soon after we will combine the two. So let's get started. So this chapter, we're going to go over first chapter 27. And these are the learning outcomes for this chapter. We're not going over all the sections, okay? So these are the sections we're going over right here. We're going to first talk about the properties of magnets, how they interact with each other. So we're going to qualitatively talk about magnets. And then we're going to talk about the force that a charged particle feels when it's in a magnetic field, right? So magnetic fields create a force on moving charged particles. Then we're going to describe the magnetic flux through a surface, right? Analogous to electric flux, so that shouldn't be too bad. And then describe the motion of charged particles in a magnetic field and finding the magnetic force on a conductor, right? So in the first part, we're going to just talk about finding forces on charged particles, and then eventually, instead of talking about just a single particle, we're going to talk about basically current carrying a wire, okay, and the force on an entire wire. So watch this video if you're self-studying, okay? He's basically going to go over the next few slides. So if you like his explanation better, you can just listen to that and skip the next few slides, or you can listen to me. So let's describe some properties of magnetic objects. And the magnetic object that we're going to talk about is a simple bar magnet, okay? For example, like a refrigerator magnet, or the bar magnets that, we really don't use bar magnets anymore, so you may not have, ever encountered. Maybe you've encountered a neodymium magnet, which is like a little cylindrical pellet-looking magnet, okay? Well, any of these magnets, they have poles, okay? So every magnetic object has a north pole and a south pole. And in general, the opposite poles attract each other, and the like poles repel each other, okay? So opposites attract, like repel, same business as charged particles, okay? So that's observation number 1. Observation number 2 is, well, every magnet has the 2 poles. There is never a magnet that has only a north or a south pole, right? That's called a monopole. So there is no experimental evidence for magnetic monopoles. Every magnet or every magnetic object will have a north and a south pole. So even if you take a bar magnet and you cut it in half, okay, and then you cut that piece in half, and then you cut that piece in half, and then you continue to cut that piece in half, you will always have a north and a south, okay? It will spontaneously arise. You will always have a north and a south. You'll never have an isolated pole. So the third observation is that magnetic objects can attract non-magnetized objects, okay? So for example, this bar magnet, which has a north and a south pole, if you bring it near a metal object that is not magnetized, okay, meaning it doesn't have a north and a south pole, it's just a piece of metal, right, that itself, this nail would not attract another nail, but magnets will attract it, okay? So there's certain metals that are not magnetized, right? You can't just stick a nail on a refrigerator, it won't stay. You can't stick a paper clip to a refrigerator, it won't stay, right? It's not magnetized. But magnets will still attract those objects, okay? And that's because of a very, analogous reason to why charged objects would attract uncharged objects. So remember back in chapter 21, you had a comb, right, that you charged by rubbing it in your hair. And then as you pulled that comb away from your hair, the hair kind of like was still sticking to it, right? Well, your hair wasn't charged, the comb was. And so in this same way, this magnet is magnetized, the nail is not. However, there's still a force of attraction there. And the reason is because the magnet will kind of polarize, if you will, the iron in the nail and draw the oppositely charged areas close to the magnet. Okay, and so you'll get that force of attraction. So that's the third observation. Oh, here's another observation, right? What about a current carrying wire? So I briefly mentioned that, moving charges cause magnetic fields, okay? And so what do compasses do? So we're going to use this compass as a magnetic field detector, right? Because the purpose of a compass is to detect magnetic fields. It detects Earth's magnetic fields. So depending on where you are on the Earth, this little needle will, point towards north, right? It'll move around. It's a jiggly little needle. So if you put it near a wire with no current flowing through it, okay, no moving charges, right? Nothing's moving in that wire. You'll have no movement of the needle. But if you now send a current through the wire, let's say going up, you'll suddenly get a deflection of the needle, letting you know that a magnetic field is present. And if you send the current the other direction by applying a potential difference in the opposite polarity, you'll get a deflection in the opposite direction. Okay, so these are observations here. And so these observations are leading us to a statement. The statement is that moving charges create magnetic fields in the surrounding space, okay? And that magnetic field exerts a force on any other moving charge that is present in the field. Similarly to an electric field, a magnetic field is a vector field, okay? It's a vector field. What is a vector field? A vector field means that any point in space, you're going to have a magnetic field vector. And then you're also going to have an electric field, right? You're going to have an electromagnetic field. We're just talking about magnetic fields right now, right? We're forgetting about E for now. But any point in space, you'll have a set of vectors that describe the magnetic field at that particular location. That's a vector field, okay? And the symbol B is what we'll use to describe that vector for a magnetic field. So how do we define the direction of B? Well, the direction of B is defined as the direction in which the north pole of a compass needle tends to point. Okay, so if we kind of scroll back up here, we look at this situation here. What's the direction of the magnetic field? It's going to be just like this. The direction of the magnetic field at this needle, in the average area of this needle is going to be this way. And then in this picture, the magnetic field direction in this general area here, averaging, okay, is going to be in this direction. All right? So if the direction that the B field points is the direction that the north pole of a compass needle would point, okay? The unit for magnetic field is the Tesla, okay? 1T. And the Tesla can be written in SI units as a Newton meter over ampere. So let's do some more observations, okay, before we get into the math. Here's an observation on the force, the magnetic force that a moving charge feels when it's in a magnetic field. Okay, so we have a magnetic field B pointing to the right. All right, we have two charged particles. One's moving in the direction of B, the other is moving anti-parallel to B, okay? Well, anytime charged particles move parallel to the magnetic field, they don't feel any magnetic force. So they feel no force due to B, okay? The only time they feel a force due to B is when there is a component of V perpendicular to B. Okay? So the other time that a particle will not feel magnetic force is if it is at rest, right? Meaning V equals 0. So if it is not moving, it does not feel a magnetic force. So the only time a charged particle feels a magnetic force is when it has a non-zero velocity and that component, one small portion or any portion of that velocity is perpendicular to B, okay? So those are the two conditions. And those two conditions, they're kind of looking familiar, right? It's looking like a cross product, all right? And so that's exactly how we can express the magnetic force on a moving charge. The magnetic force on a moving charge is a vector or a cross product, right? Those mean the same thing. The vector product and the cross product are identical. Just two different, names for the same thing. So the force that a charged particle feels in a magnetic field, it's the cross product of the charge times the velocity vector crossed with the magnetic field vector. Okay, so if you remember back from chapter 1 in physics 1, right, cross products, we didn't talk too much about it because I knew we would be talking about it now. So if you don't remember every detail about cross products right now, that's okay. Now is the time to go back and refer to it. So cross products are basically another way to multiply vectors, and the quality of cross products is that the resulting vector of the cross product, the result, which is F in this case, is going to be perpendicular to both this vector and this vector, okay? So in other words, the plane created by those two vectors, V and B, F is perpendicular to that plane. Okay, that's another way to think about that. So the plane created by V and B, F is going to be normal to that plane. Okay? So let's kind of put all this into action here. Let's look at this example. So we have a beam of protons, okay, which each proton has charge of positive 1.6 times 10 to the minus 19 coulombs. They're moving at 3 times 10 to the 5 meters per second. Okay, so here's Q. This is V, magnitude. Okay, they're moving through a uniform magnetic field of 2 Tesla. There's our B magnitude. And the direction of that magnetic field is along the positive Z-axis. The velocity, so that gives us the direction of B. The velocity of each proton lies in the XZ plane and is directed at 30 degrees with respect to the Z-axis. So that's going to give us the direction of V, okay? Find the force on each proton. So find the force on one proton. So we're going to be doing a cross product, right? So we're going to be doing, obviously, this cross product, which means we need to figure out what these vectors are, given the word problem. So the velocity, well, the magnetic field vector, we can kind of write off the bat, right? Because it's completely along the Z-axis. So the magnetic field vector is going to be 2 Tesla K hat, right? What about the velocity vector? That's going to take a little bit more work, so let's look at it. So the magnitude of the velocity vector is 3 times 10 to the 5. All right, so that's the magnitude of this vector. And it's pointing at an angle of 30 degrees from the Z-axis. And it's lying in the XZ plane. So if it's lying in the XZ plane, that means it's going to have a, it's not very straight. I want to make it parallel to X, right? It's going to have a component in the X direction, and it's going to have a component in the Z direction. So let's redraw that so we don't have the B vector in the way. right? So if we redraw it, let me go ahead and draw the coordinates. So it's lying in the XZ plane. Okay, that's where they have their positive X and Z. The velocity vector is at an angle 30 degrees from Z. And so its X component is going to be parallel to the X axis. Its Z component is going to be parallel to the Z axis. There's our right triangle. Okay, we can use our trigonometry to figure out the components. So the components of V, so our V vector is going to be Vx sine 30, right? Because it's opposite to that 30 degrees. And that's going to be in the I hat direction, right? In the X direction. And it's going to be the VZ, I'm sorry, not VZ. This is going to be the magnitude of V, right? It's just going to be V, right? This is V. So it's going to be magnitude V sine 30, magnitude V cosine 30 K hat plus, right? They're both positive. So here's our two vectors. I'll just leave it as V sine, I won't put the numbers in yet, just because it takes a lot of space. And so now we're ready to do the cross product, right? We're ready to compute Q, which is a scalar, times V cross B, okay? So there's a couple different ways you can do a cross product. You can use the determinant method, all right? And the determinant method, you may recall me explaining it to you last semester. I'll show you real quick where you can get a short video that fully explains how to use it. It's right here. Unit 4. Okay, there's a lot of really good videos. You should probably go through all of these because, I mean, magnetic fields and forces is going to be a particularly difficult section. So right here, the easiest way to compute a vector cross product, that's going to take you to this video, okay? So watch that video, watch any related videos if you don't understand it. But that's basically the method to do a cross product using the determinant method. So we can also just kind of do it algebraically. So let's look at that. We'll do it the way that it's done in this link right here, right? Which is another solution to this example. So when we compute QV cross B, right? Let's kind of write it. Let's write it all out algebraically. So F is going to be QV cross B. Q is 1.6. V is going to be V sine 30 I hat, V cosine 30 K hat, cross 2 K hat. Okay, so the rules for cross product is that same directions crossed each other equals 0. Okay, so K hat, so basically what we're doing is you're just distributing, right? We're basically going to rewrite this as a distributing this cross this guy and then this cross this guy. Okay, so let's do the distribution. Let's do it algebraically. Let's continue on so you can really see that. I'm just going to rewrite this as Q for now to save me some room. So this can be rewritten as V sine 30 I hat cross 2 K hat plus Q times V cosine 30 K hat plus 2 K hat. Okay, right, I just distributed the cross product. Okay, oh, that's a cross. That's a cross. And then the rules for cross product are that the same directions cross each other equals 0. So this term is going to come out to 0. And so basically all what we're left doing is this first part right here. So the force is going to be Q V sine 30 times 2 Tesla I cross K. Okay, I cross K. You can look up in the back of, or in chapter 1, what is I cross K? Well, I cross K is negative J. Okay, I cross K is negative J. I can show you the trick for that too. So basically, if I'm just gonna write B, right? So we can kind of see it's QVB sine 30 in the negative J hat direction. Okay, so plug in those numbers and you should get, I had the number here, but I lost it. Here it is. 4.8 negative 4.8 times 10 to the minus 14 newtons in the K hat or the J hat direction. Okay, and the negative sign I put here. You can either put the negative sign here, or you can put it with the J direction. Okay, in other words, this is also true. Okay. So, and so let me show you this trick of how did I know that I cross K was negative J? How did I know that? So here's the second cross product trick. Okay, the first cross product trick is in that YouTube video. The second one I'll show you up here. So we basically do IJK, okay? And we draw little arrows going in the clockwise direction. And then I'm going to do another set of IJK with the arrows going in the counterclockwise direction. And you get a positive here and you get a negative here, okay? So if I am crossing, so what we were doing I cross K, okay? So that's me following the arrow from I to K. That's going to make my resulting direction in the negative J, okay? In the negative J hat. So if I was going the other direction, for example, I cross J is positive K, J cross K is positive I, okay, K cross I is positive J. If you go counterclockwise, you get the negative. I cross K is negative J, K cross J is negative I, J cross I is negative K. All right. So that's how you know if your direction is positive or negative. It's if you're going clockwise or counterclockwise with the coordinates, okay? With the positive coordinates. So, so this is kind of this example. It's basically you're just using QV cross B, and you are revisiting your cross product rules from chapter 1. So there is a right-hand rule, right? You can use your right hand to give you the direction of the force, right? And it's doing the same thing as this stuff right here. Okay? So to figure out the right-hand rule, you need to place your two vectors that you're crossing, right? Your V and your B. You're going to place those two vectors tail to tail. Okay, and then you're going to imagine, so for example, let's just say V is this way and B is this way, okay? Put them tail to tail. And then imagine turning V towards B, okay? Imagine moving V towards B, keeping those two tail to tail, all right? And the force then would act along a line that's perpendicular to the plane created by V and B, okay? And you would curl your fingers in your right hand from V to B, which would put your thumb pointing into the page. Okay? Your thumb would be pointing into the page, curling your fingers from V to B, and that your thumb direction is basically the direction of the force. Check out this video for, to see the hands moving, okay? You can't see my hands right now, obviously. Here's some hands, right? See if that helps you visualize this. So if you look, you see the fingers here are curling from V to B. And to do that, your thumb would need to point up. But to curl V to B in this way, right, you naturally have to rotate your hand so that your thumb moves down and points down, right? In order to make that curl happen. There's no way to make curl V into B with your thumb pointing up, right? It's not possible. You'd be curling B into V, but you're not. You're curling V into B, right? Velocity into magnetic field, and that makes your thumb point down. So, everything we just talked about for the right hand rule, that was for a positive charge, okay? What if that charge is negative? What happens? Well, the force flips, okay? The force direction has a negative sign in there now, right? That was inside the Q. So that makes your force point in the opposite direction of the positive charge, okay? So you do the right hand rule. So when you're doing a negative charge, okay, you're finding the force on this negative charge in a magnetic field pointing to the right. Okay, you use your right hand rule, sweep V into B, and then you remember to flip your thumb at the end. Okay, so if you do the right hand rule, flipping V into B, your thumb is pointing up. Okay, but since it's a negative charge, you're going to flip your thumb, I cannot draw this, right, upside down. So another idea is for negative charges, you can use your left hand. Then you don't flip, okay? So left hand rule, right, curling V into B would be your thumb pointing down for the top picture. To curl V into B with your left hand, your thumb would be pointing up, okay? So you can use your left hand for negative charges. Use your right hand for positive charges. So imagine two charges, same magnitude, opposite signs, okay? They're both moving with the same velocity, okay? Meaning they're both moving in the same direction with the same speed. Well, what happens? The magnetic forces on each of those particles are equal magnitude in opposite direction, okay? This situation comes up all the time. So this is just something to think about, right? The B field pointing to the right for both particles. Velocity pointing down here for both particles. But the force they feel is the same magnitude but opposite directions. The positive particle will feel the force pointing up, and the negative particle will feel the force pointing down. Okay? So this video also goes over the right-hand rule a little bit more. It's a great one to watch just to really get that kind of complicated method down. So in this kind of test your understanding, this conceptual question, all right, let's look at this situation and figure out what direction this negative charge would follow, okay? So in this picture, the magnetic field is denoted by these X's, which means that the magnetic field is pointing into the page. Okay? The particle is negative, so Q is negative. And it's moving to the right. So what direction or what path would this particle start to float into, right? Because as it moves along this field, it's going to start feeling a force, okay? And that force is going to start moving its path, right? It's going to start changing the direction of its motion. And so which direction is that? So, well, the force that it feels is going to be given by QV cross B. Okay? And a good way to tackle this problem, well, you could just, let's go straight and do the right-hand rule. And then I will assign Cartesian coordinates to this picture, and we can look at it from that viewpoint. But for now, right, V is pointing to the right, so your fingers are going to be flat. So if I'm kind of drawing, okay, your fingers are going to be pointing in the V direction, flat, and they're going to start curling into the page, okay? They're going to start curling into the page. This is your right hand. And when you start curling them into the page, your thumb is going to be pointing up. All right? Your thumb is going to be pointing up, but remember, you're using your right hand, and this is a negative charge. So you'll need this, if your thumb is the force direction, you'll need to flip it in order to find the force for the negatively charged particle. So your force then, instead of pointing up, is going to be pointing down. Okay, so when that particle is right here, when the particle moves, it's going to be right here. It's going to start going down here, right? It's going to start feeling a force pushing it down, okay? Right? And so, therefore, path 3 is the logical choice, right? It's going to start feeling a force downwards, right? A downwards force, which is perpendicular to both B and V, right? Which that checks off with what the cross product is, right? The force needs to be perpendicular to both V and B. B is into the page, V is to the right. Down is obviously perpendicular to both of those. So let's assign some coordinates and we can really see that. So let's draw a coordinate system, a 3D like this. Let's do Z being out of the page, Y, X, okay? So if we translate this picture into the X, Y, Z coordinate, into the page would be negative Z, okay? So B would be in the negative Z direction, negative K hat. V would be in the X direction, positive X, right? And so if we do, and so what we need to do is we need to do I cross K, I cross negative K, right? So I cross negative K is what? I cross negative K, if we take the negative out for now, in other words, I cross negative K is the same thing as negative I cross K, all right? And that's because of the distributive property of -1, okay? You can put the negative here. You can just move the negative anywhere you want, right? As long as you don't add more, you can move it anywhere you want. So if we take it out, let's do the cross product of I cross K, all right? So I cross K is going counterclockwise. So that's going to give me, so I, J, K, clockwise is positive, okay? Counterclockwise is negative. So I cross K gives me negative J, okay? I have another negative sign in front. So that's negative J, negative J is J. But then, since we are doing a negative charge, right, we have another negative sign from Q that we need to take into account, which brings us back to negative J, all right, which matches what we found using just our hands, okay? So when you do it algebraically like this, you have a lot of negatives flying around, all right? We had 3. So you need to be really careful with that, but some people's brains work better seeing every single detail, seeing every single negative, where the negative disappears to, where it comes back from, okay? And some people, they'll trust their hands. You'll just do it, and the hand is the right answer, so they're going to go with it. Just, you have to remember to flip your thumb when you're dealing with negative charges. So we did it both ways. We got negative j hat, right, which is in the negative y direction. So, right, the three negatives, the first negative came from the fact that B is in the negative k hat, okay? The second negative came from the fact that we did I cross k, and so we had to put that negative back in, right? I cross k is negative j. And then the third negative came in because q is negative, okay? So that's how we ended it back up with negative j. So, there's let me show you a great video for doing more problems like this, because this is a great exam type problem. So if you go here, back to Unit 4, okay, this playlist right here. So, right, look at all those different
Welcome
orientations.
to iLecture Online, and today we're going... Welcome to iLecture.
You can see all the stuff that my child, well, I watch some of these. My child watches the Garfield and the Going Balls gameplay, but the rest is all me. So this playlist
Welcome
right
to
here.
iLecture Online, and here's another example of how you figure out...
And he does a whole bunch of examples. Let me just mute him real quick. And that's not the one I wanted to show you. This one, the first of the playlist right here. All right, you can see V and B in every single orientation, and you go through and you figure out what is the direction of force for all these different orientations. Okay, so start off with video 1. This is excellent video to help you summarize and generalize questions like this one. Okay, so if you struggled with this, do some practice on those YouTube videos, and then also the practice quiz section in Mastering Physics will have questions like this as well. All right, so let's talk about briefly, magnetic field lines. So remember, we looked at electric field lines in some detail. We didn't really talk too much about it. And we're not really going to be treating magnetic field lines too seriously, but all I want to really illustrate to you is the direction of those magnetic field lines, right? And how they point in the direction that the compass, the north, would point. All right, so that's what those little pictures there show you. So magnetic field lines have some properties, right? The first one is they never intersect. Same thing for electric field lines. And the magnetic field vector on these lines, right, they're tangent to, the magnetic field vector at this point is the tangent to that curve, okay? So the magnetic field vector right here is the tangent to this curve, okay? So that's really what, and the other thing I wanted to tell you about this picture is that the North Pole, right, magnetic field lines leave the North Pole and enter the South Pole, okay? They point away from north and point towards south, okay? They point away from north and they point towards south. So let's generalize a little bit. Instead of talking about a single charge, right? Let's imagine many, many charges flowing together in a current along a current-carrying wire. So here, the yellow wire here, right, has a current flowing this direction. And the question is, what is the magnetic field direction around this wire? And that direction is given by the right-hand rule, but a different one. So the right-hand rule for determining a magnetic field direction, right? Before, the right-hand rule was for force. We're switching gears a little bit. We're looking at the magnetic field direction. Okay, not the force, but the field being created by the current carrying wire. And so what you do is you point your thumb in the direction of the current, and then you curl your fingers. Let's see if I can draw curled fingers. Oh, that's nice. Thank you for helping me. Right, curled fingers. Your fingers will curl in the direction of the magnetic field, using your right hand, of course. Okay, so that's one view, the perspective view of this current carrying wire. So what if you're looking straight on at the edge of the wire? Well, then what you would see is you would see magnetic fields coming out of the page at you above the wire and into the page below the wire, right? In order to make that curl, right? Directly above the wire, if you're looking straight this way, right, you're just going to see little arrow dots coming out at you. And then directly below the wire, you're going to see the little tails of the arrow. Okay? And so we need to know this because it's going to be helpful when we get to finding the force on a current carrying wire. Let's talk about magnetic flux now. All right, magnetic flux, analogous to electric flux, right? It's how much of a field is traveling through some area, okay? And the amount of field that we care about is the amount that is perpendicular to the area, right? In the same way that we defined electric flux. This integral is exactly the same, except we have a B instead of an E, okay? However, the Gauss's law is not the same, okay? The left-hand side of Gauss's law for magnetic fields is analogous to that of electric fields, but the right-hand side is always 0. So the total magnetic flux through any closed surface is always 0. And so why is that? Well, I'll tell you why. Remember, magnetic objects always have a north and a south pole, right? So if we extend the analogy, and the analogy being the north pole is positive charge, then south pole is negative charge, okay? Anywhere, if you place a magnetic object inside of a closed surface, you basically have those charges canceling and therefore no charge enclosed, right? So anytime you put a magnet inside of a box, the flux through that box is going to add up to 0 because the magnetic field lines coming out of the North Pole will cancel out the field lines going into the South Pole, okay? And so that's why the right-hand side of Gauss's law for magnetism is always 0. So the unit of magnetic flux is a Weber, which is a Tesla per meter squared. Okay, not per, sorry, a Tesla times meter squared. Another unit for magnetic field is Gauss. So there may be 1 or 2 problems that use Gauss. Okay, so here's the conversion for that. But that's the unit of magnetic field, right? It's either Tesla or Gauss, but the unit for magnetic flux is 1 Weber. Okay, it's a Weber, which is a Tesla times meter squared. Okay. So here's another example that we can do that basically practices flux definition again. I'm going to let you guys do that because it's literally analogous to electric flux. So you're going to be doing all the same mathematical operations, except you're using a magnetic field instead of an electric field, okay? The only time where this analogy falls apart is when we're talking about Gauss's law, right? Because Gauss's law for magnetic fields states that the flux through the surface is always 0. Whereas the Gauss's law for electric field states that the flux through the surface is equal to the charge enclosed over epsilon naught. So I'll let you guys do that.